Welcome to the Understanding NDI Switching Architecture module of the NDI Basics track. In this module, we'll be diving into the fundamentals of NDI switching architecture, focusing on recognizing the switch configuration functions which are often applied by user-friendly setup applications. We'll also introduce the complexities of IP networking and highlight the need for increased knowledge of networking over SDI when deploying NDI. This is a basic level introduction, but we'll be elaborating on this in further detail, of course, in the NDI Advanced. But for now, by the end of this module, you'll have a solid understanding of these key concepts, setting the stage for more advanced learning. Let's begin by exploring the switch configuration functions, which are often applied by user-friendly setup applications provided by switch manufacturers. Now, these applications do simplify the process of configuring network switches for NDI workflows. That makes it accessible for even those without extensive networking knowledge. However, while they are effective to quickly manage the configuration of your switch, it's not necessarily an altogether complex set of processes thanks to the networking versatility of NDI. Options such as enabling IGMP snooping are essential for managing multicast traffic efficiently. However, it's important to remember that NDI uses unicasting by default, as this is the de facto standard for networking communication between any data endpoint devices. An NDI device will only multicast when multicasting is requested by the sender. Otherwise, it'll use unicast. Hang on though. Matt, let's back the truck up here a minute. What do you mean by unicast and multicast? It's a great question. So let's clarify it. Unicast is a one-to-one communication. That's where a single sender transmits data to a specific receiver. In AV over IP, unicast is ideal for private streams between devices, but it can become inefficient if multiple receivers need the same stream, because it requires duplicate transmissions for each receiver. And that's where multicasting can help. You see, multicast is a one-to-many communication model. It allows one sender to transmit data to multiple receivers that have joined a specific multicast group. For AV over IP, multicast is often preferred for sending the same video or audio stream to many devices, in other words, multiple displays, as it reduces bandwidth usage compared to unicast. The data is only streamed upon request, unlike broadcasting, for example, because broadcasting is a one-to-all communication, where data is sent to every device on the network. In AV over IP, broadcast is less commonly used as it can overwhelm the network by sending streams to all devices, whether they need the data or not. Broadcast is mostly reserved for administrative tasks like device discovery, for example. When an AV controller is added to a network, it will broadcast tiny discovery packets to identify any AV endpoint devices which are online. So, while NDI is quite happy to stream using multicast when requested, it will default to unicasting because products unicast by default. Flow control plays a crucial role in ensuring real-time, low-latency transmission of NDI AV streams. Flow control is a network mechanism that manages the rate at which data is transmitted between devices to prevent congestion or packet loss. When a receiving device becomes overwhelmed with data, it signals to the sender device to slow down, to ensure that data is not lost due to an overloaded buffer. For NDI, which requires high reliability and precision for bidirectional two-way communication, symmetrical flow control is preferred. This means flow control is enabled in both directions, allowing both the sender and receiver to manage data flow efficiently. NDI's bidirectional nature means that not only is video and audio sent from one device to another, but feedback like metadata or control commands are also sent back. Therefore, symmetrical flow control ensures that both streams, audio, video, and control signals maintain a stable connection without congestion on either end. Now, many network switches have the option to enable something called jumbo frames, and some have this option enabled by default. Jumbo frames refer to Ethernet frames larger than the standard 1500 bytes, typically allowing a maximum of 9000 bytes, and they're designed to improve network efficiency by reducing the number of packets required to transmit large amounts of data, which is helpful in reducing overhead and CPU usage on networks handling big files or bulk data transfers. However, for real-time AV over IP workflows like NDI, disabling jumbo frames is often recommended, and here's why. If a single jumbo frame is lost, it results in the loss of a much larger chunk of video or audio data compared to a standard size packet. And since NDI is focused on real-time video transmission, losing even a small amount of data can disrupt video quality, and that leads to noticeable glitches or dropped frames. Disabling jumbo frames minimizes this risk because with smaller packets, any packet loss results in a much smaller portion of video data being affected, reducing the impact on the overall stream. In high bandwidth real-time environments like NDI, it's essential to prioritize reliability and minimize potential disruptions, which is why avoiding jumbo frames is a best practice to maintain smooth, uninterrupted video streams. VLANs, or virtual local area networks, are there to help segment network traffic, isolating NDI streams from other network activities, for example, and this can remove potential interference and improve overall network performance. Additionally, the application allows for easy management of bandwidth allocation to ensure that sufficient resources are dedicated to those NDI streams to prevent congestion and latency issues. As many integrators turn to VLANs to better manage network traffic on larger networks, we'll explore VLAN setup and configuration in the NDI Advanced course. But for now, let's remain focused on the efficient setup of our NDI network across a single network with no segmentation.
Deploying NDI involves navigating the complexities of IP networking. But while this can appear to be more challenging than traditional SDI setups, understanding these complexities is not the upward battle many people consider the switch to NDI believe it to be. Unlike SDI, which uses point-to-point connections, NDI relies on IP addressing to identify and communicate with devices on the network, and with a good basic knowledge of IP address allocation and management, you'll be up and running in no time.
In summary, understanding NDI switching architecture involves recognizing the optimal switch configuration needed and grasping those complexities of IP networking. We've introduced you to some of these key concepts in this module and highlighted the need for increased network knowledge when deploying NDI. Stay tuned for the next module where we'll be looking at NDI discovery and registration. But in the meantime, don't forget to take the short quiz to test your knowledge of what we've learned so far. See you soon.